much for joining us here today. This is Paul Taubman with 9.connects. You are in the right place if you are here for our webinar on cool antenna. Too bad it was not intentional. Our presenter today is Sean Kelly, and Sean has presented with us several times before on topics of this nature. And since he does have a lot to cover today, I'm going to turn it immediately over to him. So Sean, you have the floor.
Okay, well, thank you all very much for joining us again today. And so one of the things I want to get into exactly is the purpose of this webinar. So in order for you to understand why some things are antennas and even though you're not expecting them to be such, we have to talk about some antenna principles. We're also going to talk about what makes a good antenna. And then we're going to talk about different structures and why they act like antennas, even though you're not intending them to be such. And then lastly, we're going to talk a little bit about mitigation techniques. As always, if you're interested in learning more about this presentation or anything else, feel free to reach out to us. Before we get started, I would like to ask a quick polling question. Okay, so it looks like just want a better understanding of EM fields in general. Well, good. Okay, so let's go ahead and get started on the next section, which is the review. So the first part that we're going to talk about in the review is going to be transmission lines. We're also going to talk about scattering parameters, wave propagation, and then reference plane versus ground plane, which is one of my favorite subjects, because there always seems to be a lot of confusion about that. There are several previous webinars that are going to be covering much more in depth some of the material that we're going to be reviewing today and using. And if you'd like to see those, just again, reach out to us, ask for webinars dealing with transmission lines, enough with high speed already, or what does a simulation give you? So the first thing we're going to talk about is scattering parameters. So the question is, what exactly is a scattering parameter? Now this, I could do a whole webinar just on this, but suffice it to say, we're going to just cover this very quickly so we can get into the meat of the subject. So basically a scattering parameter is a way to demonstrate the ratio of one wave's voltage to another wave's voltage. And in this situation, we're going to be talking about S21, which is a very common nomenclature to describe the throughput of a system. S11 describes the reflection of a system. Microstrip is going to have both, and we're going to be using Microstrip as part of our comparison to antennas, and so you'll need to understand S21 as that is related to the Microstrip. Microstrip also is typically going to have a reflection because your source may be seeing a microstrip with an impedance that's different. So we'll get into that. For antennas, though, we're mostly concerned with the term called S11, the reflection, because ideally we don't want any energy reflected from an antenna. We want the antenna to be able to radiate everything that it is getting from a signal source. In essence, what an antenna or a scattering parameter does, let's see, I want to show my laser pointer here, is if you're looking up here, this is a concept of a two-port network where your signal is coming in to the port as a signal A1, and some of the energy goes through, and that's why you have S21 showing here as the signal going through your system or your device under test. Then there's always going to be at least some energy that's reflected back toward the source as wave B1, and that's why we term the reflection as S11. And you can see up here, here's the equations for the different terms. The amount of reflection is going to be a ratio of B1, which is your reflected energy compared to the energy coming into the system. Obviously, we want to make sure that we want to hold A2 equaling 0, which basically means that we're not looking at any signal coming from the load, which would be coming in port 2. That's going to be really important for the antenna concept. So the next section we want to talk about is how does a transmission line actually propagate? So On the left-hand side here, you see a voltage supply using a step voltage, and we're going to turn this voltage supply on. And so we're going to be applying a positive charge to the top line and a negative charge to the negative side, or the bottom side. So if you froze time just after you applied the step voltage, and you could use a voltmeter to measure the voltage at different points along the line, you would end up seeing a graph of points that form a wave, hence the concept of this right here. So if we stop the step voltage in time, and you could actually take a multimeter and measure across these two conductors, you would see that this charge that is actually moving down the line takes time to do so. So as time will then continue, this distribution of charge is going to continue so that the voltage differential appears to propagate to the right. In other words, from the source down to the load. In AC wave behavior, think wave, not current. A lot of us, when we first get started looking at transmission lines and understanding them, we're thinking about current. In the DC analysis, we use the step model voltage source. But in an AC analysis, it is much easier to demonstrate the concept, especially visually, if we think about a sinusoid. And so what you have here on the left is a top view of what energy is propagating as an electric field down the transmission line. The right-hand picture you see is that the electric fields that exist between the top conductor, which would be a microstrip in this example, and then your ground plane or reference plane underneath it. See, I've caught myself saying ground plane. It's easy to do. So now when it comes to reference planes, we need to get out of the habit of saying ground plane. And here's why. Your wave of energy is going to be composed of both electric and magnetic fields traveling. And they're going to be doing this because there's an electromotive force that is applied to these conductors. That EMF is not going to care at all about a ground. It only cares about the positive terminal and the negative terminal. Ultimately, the reference plane can sit at any DC level. And in fact, you'll find as you look at more and more designs that people have done, they will actually jump the reference plane from ground to a voltage plane and back to a ground plane again. So you would be much better served not to think of current, but instead think about the moving voltage because of the current. And here's what I mean. If you picture the wave moving away from the EMF source and consisting of that E field, the electric field, between the two conductors based on the difference of potential, then it ultimately does not matter if you see the below circuit as single-ended or differential. Anything that's going to impede the wave from forming between the two inductors in a uniform and consistent manner is going to be detrimental to the concept of signal integrity. This really is probably, if you don't remember anything else out of this webinar, I want you to remember that statement, because your goal when you're trying to get a signal from A to B is to make sure that it does so in a uniform and consistent structure. So with that in mind, if you're looking at the shape of the fields in this picture, you'll see that they are due to a uniform shape of the conductor. And if you were to watch this wave propagate from the part of the picture toward you to the back of the picture, you would see that that electric field stays that same shape all the way, because what you have is a uniform microstrip and you have a uniform reference plane underneath it. Anything that changes the symmetry or uniformity will change the wave shape, and that is detrimental. Now, here's a difficult concept that you may or may not ever have seen before, but is extremely important for you to understand in order to really grasp the rest of the webinar. This has to do with concepts of return current. When we're taught basic circuits, we're taught that charges, a positive charge could leave your terminal, go through a wire, go through your load, and then it comes back through your return current path. Now, when you're at DC, there's no problem with that concept. Your charges, your positive current flow, meaning that your positive charges are going up here, they go through your load, and then they come back any way, shape, or form they want to. all based upon this concept of least resistance. And that's the key here. The problem is when you start going up in frequency, that changes. And oddly enough, or surprisingly enough, it doesn't happen at a very high frequency that you start noticing that now your return path is no longer the shortest resistance or shortest distance due to the low resistance, but actually the least amount of inductance. And so again, as you go with higher frequencies, ultimately what the wave is going to try to do by its general nature is always create a tightest electric field possible between the two current carrying conductors. Now, as we move forward in this discussion, understand that as you get higher in frequency, then you will see this charge distribution taking place, where you have charges, the majority of the carriers are actually between the microstrip and the reference plane, but then yet there's quite a significant amount out here to the side. And that's the part that a lot of people just totally ignore or not even aware of. They think of it as nice little bundle of energy traveling right here. And so they don't understand how the structures around it can influence the propagation. So if you'll notice here, we have a little diagram, 4 different scenarios where we have on the red line, it represents the current on the top layer. On the blue represents the current on the bottom layer. Now, as we just discussed, in DC, you would have this in section A, but that does not happen in high frequency. In high frequency, it now would start showing up as B. You would never see A happen in your higher frequencies. So what ends up happening is going to be dependent upon the fact that at your higher frequencies, again, I don't like to think about the return current path so much as I like to think about my positive and negative charges moving in parallel, in lockstep with each other along the path of the microstrip. So this is the way it's naturally going to want to behave. But actually the blue, I would rather the blue arrow be drawn in the same direction as the red arrow. But nonetheless, graph C here we have is actually a major problem, because if, let's say, we had a positive charge on the microstrip and we had negative charges on the reference plane, and they're all moving in lockstep to keep the electric field as tight as possible, when it gets to this gap here in your reference plane, well, that presents a problem, because your charges aren't going to want to just jump that gap. So in order to maintain the electric field, they end up having to move down here and go around that gap and then reunite to be back in sync with the charges on the top of the microstrip to get to your load. So that presents a major problem. So scenario D here is what a lot of people will do to get around this situation if they have to have a gap, and that is they place a passive component that bridges it. And so now you have the ability for your electric field to maintain the proper spacing as it moves from your source to your load. However, your goal in high-speed design is your diagram B here. If at all possible, you don't want anything to interrupt that ability for that E field to stay in a nice uniform pattern. Here's a very typical situation over here where you have one reference plane VCC1 and another reference plane VC2, or you could possibly have just a gap between a VCC and a ground. It's fine. But because return currents are based upon the frequency of operation, then these return currents can then use coupling capacitors to jump from a ground plane to a voltage plane and back. That's what we call a stitching capacitor. A lot of times you'll see this happen in, let's say, USB lines. If USB lines are going through a circuit and they need to go traverse different layers, you'll see that a lot of times people will put a stitching capacitor to make sure that those fields stay together. If you have to have a void to jump between two ground planes, even though it's the same potential, you still may use a stitching capacitor just to go between it. And I have seen situations where that is the case. So the next section is antenna concepts. The first one we want to talk about is reciprocity. Next is radiation pattern, realized gain, and then radiation efficiency. So the first one, we're not going to really deal with that too much in this discussion, but it is important to understand that reciprocity basically just states that the receive and transmit properties of the antenna are identical. Hence, they do not have distinct transmit and receive radiation patterns. If you know the radiation pattern in the transmit mode, then you know it in the receive mode. Now, the radiation pattern itself, this is a statement that kind of reads difficult. It's a spatial distribution of a quantity which characterizes the electromagnetic field generated by an antenna. Basically, we're going to describe different quantities here in just a second. Those quantities are going to be the way you measure and understand the spatial distribution of that energy. That quantity could be power flux density, radiation intensity, field strength, or directivity. And it doesn't really matter which one you use. Ultimately, the radiation pattern is going to be the same. But for our discussion, we're going to be using the radiation intensity term of U. Not really that important to know that, but just in case you see U later on, you'll understand why. So there's several different generic types of terminologies used to describe radiation patterns. The first one is isotropic, and it's important to understand this is not a real radiation pattern. It is a way for antenna designers to quantify the behavior relative to a very equal radiation pattern in all directions. Just think of a sphere. We're not going to really talk about that per se in this discussion. The next one we will, and that is a directional antenna. And a directional antenna radiates predominantly in a specific direction, and you can think like a cone, like an ice cream cone. Omnidirectional is a very common type of pattern. If you've ever seen any of your Wi-Fi routers, those little antennas that are on the back, those are omnidirectional. Their goal is to typically distribute that energy in a specific plane. Typically, it's in a horizontal plane because most people that are using their Wi-Fi are walking in that horizontal plane and they want to have nice even reception as they're walking or moving. So you can think of a donut. Now, all radiators have lobes. Specifically, the main lobe is the one that is going to define your direction, and it's going to be predominantly in the area of that your antenna is facing. Now, obviously, this is a directional antenna description here, not an omnidirectional. But you also have side and back lobes. Side lobes are typically detrimental. They're energy that you don't want in those areas. Back lobes sometimes are actually beneficial, sometimes they're not. It depends upon the type of antenna. Now, how do you get to understand the actual pattern as it exists in the real world? Well, there's two main ways. One is with a polar plot in 2 dimensions. And even though I'm showing this in a 3 dimension, I'm actually showing you that there is a plot in the XY plane, which we call the azimuthal plane. Then you have a 2 dimension is in the YZ pattern or plane, and then you have the XZ plane. And so plotting all 3 of these together kind of give you a picture in your mind of what the radiation pattern looks like for this particular antenna. Now, keep in mind, this is at a specific frequency. Don't forget that. Most of you all, if you've seen these, you've probably seen them on a piece of paper or in documentation, and they're all separate. But in your tool, sometimes they give you the ability to overlay them so you get a better picture. Another handy way to do it is in a polar plot in 3D. In this case, it gives you a very good definition visually of what your radiation pattern looks like in all 3 dimensions simultaneously. Again, it's one single frequency. The next term we need to talk about is radiation efficiency, and that little E there is basically used to describe the efficiency in which an antenna converts the RF power. Now, obviously, the idea is you want to convert all the energy that it gets into a radiated signal. So it is the ratio of the power radiated to the power applied. And you have 2 different losses. The first one is a mismatch loss. Mismatch loss is basically going to be based on the fact that the antenna is going to have some impedance mismatch to the source, but it also has a function of trying to match free space impedance, which is 377 ohms. So what ends up happening is an antenna is nothing more than a transformer, and therefore it is an impedance matching network between, let's say, your microstrip or coax to free space. The next one is dielectric and conduction loss. Both of these are basically conversion of heat. I'm sure you're pretty well aware of that when you put current through a conductor, well, that resistance converts some of that energy into heat. Well, the interesting thing about it is an antenna, the dielectric material does the same thing. Your dielectric material has a polar moment, and as you are oscillating those fields back and forth, the amount of polar moment that those molecules have then have to rotate back and forth, and they generate heat as the molecules oscillate back and forth in order to match the electric field. Kind of think like how magnet dipoles will oscillate in a magnetic field, same concept. But because we're talking about efficiency, no antenna is perfect, therefore it's always less than 1. So the next thing we want to talk about is antenna gain. We have incident power, which basically says power in to your antenna. We call it power incident. When we use 1 watt as a generic term or a value and then measure things relative to that generic or that standard. Now, accepted power is the power that the antenna has based upon how much energy was reflected coming into it. If you remember in the discussion before, we talked about this term S11. So if your antenna is perfectly matched to your coax or your microstrip, well, then your reflection is 0. Therefore, your incident power times 1 is the same thing. So the more energy is reflected, the less power the antenna sees in order to radiate. And then the radiated power is going to be even less because it's going to take the amount of accepted power and then you're going to be multiplying it times the radiator's efficiency. So you have mismatch loss and then the efficiency of the antenna. And these gains are calculated as follows. You have realized gain, you have regular gain, and then you have directivity. The thing is, we're only going to talk about realized gain. The goal of this subject in today's webinar is not worried about how efficient the antenna is in creating power. We're trying to make sure that you understand the differences between a circuit that's not supposed to be an antenna versus a circuit that ends up being an antenna. The gain and directivity accounts for loss. And again, I'm not worried about the loss in my circuit in this webinar. So as we move forward, I'd like to ask you one more polling question, if you don't mind. Okay, so quite a few of you all picked all of the above. Well, what I was hoping is that you caught my emphasis on B, the correct answer is the distending of the fields. And maybe I didn't clarify the question. I want to talk about signal propagation of a microstrip, of some type of transmission medium. What is going to keep that propagation from taking place the most? So maybe this will start helping you to understand the question a little bit better. So let's get into our reference circuit here. It's just a basic microstrip where we have a microstrip on the top, we have a substrate, and then we have the reference plane underneath. Nothing really fancy about this. In this situation, we're not worried about losses. So we set up the simulation. So we have 50 ohms in, 50 ohms out, and the transmission line is designed for 50 ohms. So therefore, all the impedances are matched. Ideal situation, there's no mismatch loss. Now, again, with a microstrip, you have an S21. So here you can see a natural curve that takes place. The higher the frequency, the more loss there is in the material. Not very bad, but this is one of the keys I want you to see. Look at the mismatch that takes place. It's very low, minus 40 and below. That's your S11. So that means there's very little energy reflected back to the source. Notice also the realized gain. This is the ability to take your energy and put it into the outside of your structure. It's pretty low, which is ideal because you don't want your microstrip to radiate. Now, as you're looking at this, I want you to understand that we're trying to show you a visual goal, and through the next 4 sets of scenarios. And what you see here is a 3D representation. Now, this representation that you see here, we maximize the range so that you see the maximum intensity to the least amount of intensity. And you typically do that in order to better define the shape. One of the things we did on this, though, is as we move forward, we're going to keep the scale the same on all the different structures so that you can see relatively how the different changes in the structure behave. Yep, so again, all following variations of this structure are going to maintain a common scale to facilitate a visual relationship. So when we actually maintain a constant scale for every structure, what I end up doing is finding out that here's the radiation pattern of this actual microstrip. Notice that we have dark blue versus lime green. Now, let me just say this. This image is not a specific point. This is a far field, and we're not getting into far field versus near field, but basically this is generally the shape of the energy being radiated from this structure, let's say a foot away or 2 feet away. And so the blue means that you have a very weak signal, and the lime greens means it's a little bit more intense. You can generally see a little bit the fact that there are lobes involved here. Again, we're only looking at a single frequency in this presentation at the moment. So the conclusion here is you can see with your well-matched ports that your structure is also well behaved and you have minimal radiation. And the concept of minimal radiation will really make a lot of sense as we move from ideal to the worst situation. So we have one more polling question, if you don't mind. And what was the goal of this webinar? And the reason, and it may sound kind of silly to ask this question, but it's important because as we go through the rest of this webinar, having that goal in mind as we move from slide to slide is very important because they all build on each other. Awesome. Yep. I was hoping you would say that all of the above is the correct answer. Okay, so now we're going to take a microstrip with a 90-degree bend. Nothing fancy, we just made it turn a corner. And so now our load is over here in the right corner in the positive Y direction. It does have a sharp turn, so you may be want to pay attention to that. So when we do that, I want to show you how this compares to what we had with the no bend situation. So here again, here's the graph of S21 and S11 without the bend. Now with the bend, notice the S21 really hasn't changed a whole lot, which is what I would have expected. But notice now that I have more reflection. So, and it is frequency dependent. The higher the frequency, the more you get reflections from that sharp bend. Now, when it comes to realized gain, here's an interesting thing, is that oddly enough, I don't get a whole lot of difference in the radiation itself. And when we look visually, you actually see that. So here's the radiation pattern with the 90-degree bend. Looks pretty similar, doesn't it? Again, a lot of dark blue and a little bit of lime green. Again, the image is of a far field and not a specific point, even though you might think that since I have it down here in the corner. Conclusion, we still have well-matched ports. This is still 50 ohm, this is still 50 ohm. Still a fairly well-behaved structure, still minimal radiation. And then if you want to look at a close-up of how does this actually compare to the straight microstrip, pretty similar in shape, although there's not as deep a lobe in between the far field, but generally speaking, almost the same amount of energy. Now, what's interesting is this is the basis of the inverted F antenna. See how more uniform this is? So here's an inverted F antenna. This is a planar monopole with a counterpoise. Your counterpoise is basically this ground plane. This ground plane serves as the other half of a dipole, so the combination creates a half-wave dipole. And if you're familiar with that, then you know that creates a nice radiation pattern that's as uniform as possible. The result is a somewhat omnidirectional antenna. Now, it's not perfectly, but it's pretty close to it. It's one of the reasons why they're used so often. Okay, now that we got that out of the way, let's talk about what happens if I remove the sharp curve and make it a 90-degree curve instead of a sharp bend. So with a bend versus a curve, you can see again the S21 really hasn't changed much, which is what I would have expected. But notice now without the bend and the curve, my S11 has gone back down. So the reflection has decreased. That's good. Going back to the realized gain with the bend, with the curve, radiation pattern really has not changed in intensity at all. Again, you see almost identical as to what you had before. Dark blue and lime green, conclusion, well-matched ports, well-behaved structures, again, minimal radiation. Question is, how much change is there? If I blow it up and look, almost imperceptible change. So the shape of the corner here is not important as to the radiation behavior. Now, it's important to understand as we move forward that all three of those structures basically had the same S21. The S11 is basically the same for the straight and curved version. However, the sharp corner version had some greater reflections and was less stable. In all these previous examples, we had a uniform reference plane. And here is where we get to the meat of the subject, because a lot of times when people are doing board layouts, they don't always know and understand the repercussions when they have slots underneath their transmission line. And so they actually start creating a really neat antenna, and they don't even know it. So what happens when you don't have that nice uniform contiguous copper type of reference plane? Go back to what we talked about in the beginning when we said that EM field perturbations are a problem. So next we're going to look at something everybody doing high-speed routing is told to avoid. However, most don't really have a solid understanding of why. So before we go any further, let me just do a real quick reminder here. The energy that is between a microstrip and the reference plane is not all just underneath the microstrip. Most of it is, but a lot of it's not. That's very important as we move through the rest of this discussion. And anything that's going to impede this nice even distribution in the cross-sectional aspect is ultimately going to distort your electric field. And we all know what that means. Well, hopefully you will by the end of this webinar. So now we're going to introduce this minor defect. This is cool antenna number 1. So we put a defect in the reference plane underneath. There's a slot there. And so what ends up happening, even though this is not a typical problem, what happens is you have your charge carriers are still flowing in this direction, but when they hit this slot, they are now not flowing in the same laminar distribution as they were before. What ends up happening is you get some on this left-hand side, which is in the minus Y, because there's a Y axis. In the minus Y section, these charge carriers are bunching up because they can't move like they want to in order to stay in lockstep with the charges in the top. So now we're going to use a curved microstrip scenario as our reference because that was the best behaved. But when I add a minor slot, notice again, my microstrip did not create a whole lot of loss. Okay, it's pretty much the same shape, but notice now my reflection went back up again. That's not good. Now I want to look at realized gain. Here's our reference, our curved microstrip. Now with the minor slot, wow, you could really see how that thing is climbing when you go up to higher frequencies. So when we look at the radiation pattern, now you can see a huge jump in intensity. Now you can see why we kept the same radiation scale, throughout this endeavor, because now you can see visually the impact that has taken place. There are some lime greens on the back side, but there's an awful lot of reds and oranges, which is close to the maximum of our scale. So the conclusion is the majority of the radiation is going to be caused from the front side of the slot. Remember, the energy is trying to propagate in this direction, and so it's being reflected back. That's why this side is higher. And obviously the radiation itself is now much more intense. How much more? Well, just wait. Now we're going to introduce what people see on, I see it all the time when I get to review people's circuit boards, is this concept of a major defect, where you have a slot that goes all the way across almost all of the area in which the charges are going to be trying to move through. This is a very typical problem. And so what is the impact going to be? The problem is the majority of your electrons are not flowing in the same laminar distribution like we saw in a couple of slides ago. Now the electrons are going to have to move around this slot. They're going to have to end up going way out here to the positive Y direction in order to come back. No, they do not just cross over here and create a new hypotenuse. So when we look at the S parameters, again, this is our reference. With a major slot, oh my goodness, look how the S21 has just dipped. Because ultimately, what is looking at your S11? You have a lot of reflection. Well, if the energy is reflected back to the source, then I can't have it at my load, because it's a zero-sum situation. If I reflect all my energy back to the source, I have no energy at my load. Again, we're going to look at the realized gain, and notice how we're up here on our reference, but now with the major slot, now we can kind of get an idea of just how bad this thing is going to radiate. This is going way high. Now, understand that when people are designing antennas, the general rule is anything below a -10 will serve its purpose. We try to shoot for -20. But anytime you get above a -10, that's when you have major problems. Here's -10 right here. Now look at the radiation pattern. Notice how it's so well distributed in energy-wise. It's almost an isotropic situation. You almost have very little lime green and a lot of reds and oranges, which means that you have very shallow lobes being created. The lobe is very shallow here. So the conclusion is you have a very full field, your radiation is maximized. So now the question is, why is this more of a problem than the obvious? Now, if you remember correctly, we talked about this pattern is only at one frequency. So if I show you what it looks like over all frequencies, and we're going from 550 megahertz all the way up to 10 gigahertz, you can see just how uniform this pattern ends up being the higher in frequency you go. Now there's a little bit greater intensity up here in the beginning, at the front of the lobe, right here at mid frequencies, but it becomes nice and uniform. So when it's more uniform, that means it's easier for everybody in this, every structure around it to see the signal. Okay, I got another polling question. And this might be a tricky question, but what antenna is based on the microstrip behavior that we just discussed? Okay, so a lot of people said 68. And so what I wanted you to understand is, yes, the radiation pattern is somewhat of an omnidirectional, but it's more a representative of a common known antenna called a Vivaldi. A Vivaldi is a type of slot antenna. This is a generic type of term, slot antenna, and that's what we basically created in the previous cool antenna number 2. In this situation with the Vivaldi, though, you have a microstrip that comes across the top, and on the bottom, which would be your reference plane, actually creates an aperture that does a transformation of impedance matching to the antenna. And so you're coupling energy on purpose from your microstrip on top into this void in your reference plane underneath. and all this energy then comes out this horn, so to speak. And the net result is you create a radiation pattern like that. Very, very strong and very directing. So this is more for me than anything. I'm just curious, how aware were you about the impact of routing over a slot? Oh, well, good. I'm glad to see that quite a few people said they were already very aware of it. And then some said somewhat. Good. I'm really kind of shocked that there weren't more that said oblivious, to be honest. Okay, so the next section is mitigation. Mitigation is a subject that we could have its own webinar just on mitigation of the radiation of the signal. However, suffice to say that there are multiple ways to minimize the creation of an antenna. First of all, don't route over a slot if you don't have to. But if you have to, you can use stitching capacitors, like I said before. That will help you get your signal from one plane or one reference plane to the other reference plane. Or you can use shielding. And this is a common approach. However, the golden rule is it's always better not to make a signal than trying to stop one. Because what ends up happening is what you can do is create problems that you can't create enough of a shield for. So if you can mitigate by not creating the signal to begin with, you would be much better served. Besides, it's end up being cheaper, doesn't take up real estate on your board to solder, and cost. So in summation, the PCB layout is much more difficult to get correct than many oftentimes understand. Not understanding the physics of your signal propagation will oftentimes lead to the following: unwanted coupling of signals between structures. And we didn't really get into this, but that radiation that we saw, yes, it creates problems with your FCC testing, but that same kind of energy can then also be picked up by your other structures in your circuit, hence the concept of crosstalk. So when you create unwanted antennas, you're radiating frequencies that are more powerful than what the FCC allows. The FCC actually calls these unintentional radiators, oddly enough. And if you are not aware of the problem, then what you can end up doing is failing your FCC test, which could be quite costly. Don't be afraid to ask if you have any questions and need to try to understand better what your circuit is doing before you go to an FCC test. Your test will typically take 3 to 6 weeks and end up costing you $3,000. And if you haven't, kind of gone through your design and made sure that you haven't overlooked these kind of situations, you may end up having to waste that money and time just to find out you failed, have to come back, evaluate, fix, and then go back, pay another $3,000 and wait another 3 to 6 weeks. So before we get into the question and answer period, would like to know your opinion of the material today, if you don't mind. Okay, good. Thank you all. I really appreciate the kind words. That was relevant for what you needed. I'm always glad to be able to give you what you're looking for. Now, Paul's going to take over for a minute while we review some of the questions.
All right, thank you very much there, Sean. I'm going to just bring up my screen over here so we can take a look here. I'd like to talk to you for a minute about 9.connects, and you're here for a reason. So most of us are experts in designing accidental antennas. It's one of those things that we pick up along the way that we don't intend to. If you've ever played a sport before, there's probably always some little habit that you've picked up that maybe impedes your progress in becoming better in whatever you're playing or trying to perform. And so it's just non-common. It's just one of those things we picked up along the way. And we also want to learn how to unlearn how to create accidental antennas. And that's what Sean was trying to show you here today. So hopefully you found the aspect about, putting little cuts underneath the traces valuable to you. That's where most of the accidental antennas certainly crop up. But also, and this is one of the things we're always trying to do here at 9.connects, so we want to see the reality of the theory. And what do I mean by that? Well, a lot of us who've gone through undergraduate electrical engineering programs, especially those of us who are a little bit old school, probably didn't have the YouTubes and all the other good stuff that was out there. And so a lot of times we were very reliant on our professors or our own personal experiences to bring basically a reality to the theory. And more often than not, just simply due to time and the effort it takes to actually show real examples at that time, a lot of times we just got it in a theoretical form. And what we want to do here today, now that the technology is certainly there and the simulations are there, is to really put some reality behind what we're seeing, especially in the world of antennas, which already feels a little bit like black magic. Okay, so what about us here at 9.Connects? Well, our RF team has 40 combined years in antenna design. And really, actually, a lot of the combined years is beyond PCBs. So we're taking what we know about PCBs, or pardon me, antennas, and basically adding them to our knowledge of the PCB process. So that's where we come from on that. We also use the 3D electromagnetic simulators, the ANSYS HFSS, and we have the tools and the equipment necessary to run these. These are not trivial simulators. They really do require a little bit of horsepower to them. And not only do we have them, and not only do we have the tools in order to run the computers to run those, we also have the expertise to do it as well. And of course, we have our extensive experience in PCB layout and signal integrity issues. So it all builds upon each other. If you want more information about what we're capable of doing, then please do check out our website, 9.Connects. If you go to our engineering services link at the very top or in our menu here, if you go down to the side menu, once you're in engineering services, you'll see this one that's called RF and antenna. And we give a brief overview of what it really takes in order to set this up on your own accord if you're interested in doing that, and also what we can provide as well. So there's obviously tools and equipment that we have, and we make that available so you can see what we've got to offer you. And with that, thank you very much again, and enjoy the day. Take care.